So welcome to Kin 425 during the COVID crisis of 2020. This will be the delivery of the remainder of the course remotely. So I'm going to pick up on the topic of altitude and exercise from last day. And this is one of the slides that I posted last day, and it just shows the normal partial pressure at sea level that you'd get for oxygen in the inspired air and then your alveoli. So the amount of oxygen that gets into your lungs is determined by the driving pressure, or the difference between this partial pressure and this partial pressure. So what happens at altitude, and this is a bit of a review. First of all, I'm going to go to the whiteboard here. So at sea level, you have a partial pressure of oxygen that's equal to your atmospheric pressure, which is about 760 millimeters of mercury, times the percentage of oxygen in the air is about 21%, so 0.21, and that's equal to about 159 millimeters of mercury. So that's what you see at sea level, and that's what you have in this diagram up there, is 159 millimeters of mercury for partial pressure in the atmosphere. Now what happens at altitude is that you get a reduction in your atmospheric pressure. So I'm just picking an arbitrary value here of 507 millimeters of mercury. Your percentage of oxygen in the air actually stays the same, but because the atmospheric pressure is reduced, your partial pressure of oxygen, if you work out this equation, is reduced to 106 in this instant. So you have a lot lower driving pressure if this is 106 to the alveoli to get oxygen into your lungs. So this hypoxia that you experience at altitude is termed hypobaric hypoxia. The term hypobaric just means that you have a lower than normal atmospheric pressure. So if you're doing a sea level experiment and you want to simulate altitude, it's difficult to bring the atmospheric pressure down at sea level. So what's often done is that at sea level, you'll alter the gas mixture so that you have a lower percentage of oxygen in the gas mixture, and that will result in a lower PO2. So sea level experiment where you're trying to simulate altitude. Again, at sea level, your atmospheric pressure is around 760 millimeters of mercury. In this case, we're going to reduce the inspired oxygen to 14% from 21%. And that's going to give us a value of 106 millimeters of mercury that simulates what you'd get at altitude with the lower atmospheric pressure. Now, the key here is that over the years, they've conducted quite a few experiments at sea level using what's called, this is called normal baric hypoxia. Again, this is a term that we went over last day. So normal baric hypoxia just refers to hypoxia with normal atmospheric pressure, but you've reduced the fraction of oxygen in the air to 14%, and that's resulting in the hypoxia. So over the years, it's been assumed that when you simulate altitude this way with normal baric hypoxia, that it's going to give you the same physiological responses as hypobaric hypoxia. Just keep in mind that there are a few studies that are quite recent that show that the physiological responses to those two different types of hypoxia are actually a little bit different. So you don't get a perfect simulation of altitude when you do this sea level simulation with a reduced fraction of oxygen in the air rather than having a reduced atmospheric pressure. So I went over this slide last day, and it just shows that your maximal oxygen consumption, which is your gold standard for aerobic fitness, decreases quite dramatically when you go to altitude. Now this slide just shows that the decrease in your maximal oxygen consumption starts at about 300 meters in elite athletes. And to answer this question, non-athletes are actually less affected. So elite athletes seem to be more sensitive to moderate increases in altitude. Now the reason for this is that an elite endurance athlete will have a high VO2 max because they have a very high maximal cardiac output. So when they're working at maximal exercise intensities, their maximal cardiac output might range anywhere from 20 liters per minute to the best endurance athletes in the world that might have a maximal cardiac output of 30 liters per minute. This means that in those really high level endurance athletes, blood is circulating throughout the body at a rate of 20 to 30 liters per minute, which is a heck of a lot of blood to circulate in 1 minute. So what's happening is that the blood is flowing past the lungs at a very high rate, and anything that affects the delivery of oxygen to the lungs is going to have a dramatic effect with that offloading of oxygen from the lungs to the blood when the blood's going past the lungs at a very high rate. So if you're a couch potato and you have a very low VO2 max, you're also going to have a very low maximal cardiac output, which means that the blood is going to be flowing past the lungs quite a bit slower at maximal VO2, and the lungs are going to have an increased chance in that situation to offload their oxygen to the blood. So it seems like elite endurance athletes are a lot more sensitive to increases in altitude than are non-athletes. So the decrease in VO2 max at altitude, for every 100 meters above 300 meters, you get about a 0.6 decrease in VO2 max. Now, if you're measuring oxygen consumption at a submaximal workload, it is actually the same at altitude as it is at sea level, but the work at altitude feels a lot more difficult. And that is explained by this graph. So the green part of these bars represents your absolute oxygen uptake at sea level and altitude, and you can see the level is exactly the same. So this is for a submaximal work rate. Now it feels a lot more difficult at altitude because your maximal oxygen consumption is reduced at altitude. So despite the fact that you're working at the same absolute oxygen uptake, your oxygen uptake relative to your VO2 max is a lot higher at altitude. In this case, it's 67% versus 50% at sea level. So it actually feels like you're working harder at altitude, despite the fact that your absolute VO2 is the same. So your absolute oxygen consumption is the same. Now, acute altitude exposure induces a number of physiological effects. First of all, you start to feel nauseous, and your heart rate and ventilation both increase. This is probably the body's attempt to compensate for the reduced oxygen delivery to the lungs and the muscle. Now, the increase in ventilation will result in a decrease in blood volume. The reason being that when you increase ventilation, you start to blow off more water vapor. And by blowing off more water vapor, you end up reducing the plasma portion of your blood. So your blood volume decreases. That would result in less blood going to your heart, so less of a venous return and a reduced cardiac output. Now, if you have a reduction in plasma volume, that means the percentage of red blood cells in your blood will increase, not because the number of red blood cells are actually increasing with acute altitude exposure, but the fluid portion of the blood is decreasing. So the relative amount of blood cells in your blood actually increases. So you get an increase in hematocrit. And as you probably know from previous sections in the course, when you get an increase in hematocrit, it makes your blood thicker, it becomes more viscous, and it makes it more difficult for that blood to flow through the vessels. So your total peripheral resistance increases dramatically when you go to altitude. Blood pressure will increase because of that increase in total peripheral resistance. So again, if we go back to the whiteboard, recall that blood pressure is equal to total peripheral resistance multiplied by your cardiac output. So as I mentioned, your cardiac output is most likely decreasing in altitude, but your total peripheral resistance, because of that increase in hematocrit, goes up so dramatically that it drives up your blood pressure at altitude. So you get an increase in blood pressure, you also get an increase in headaches at altitude. So this increase in blood pressure can have a potentially fatal effect called high altitude pulmonary edema. So with an increase in blood pressure, you could get fluid forced out of the circulatory system and into the lungs. This will result in your alveoli filling up with fluid, and essentially it would be similar to drowning. So this could be a fatal consequence of going to a high altitude too quickly. Now, this slide deals with acclimatization to altitude, so long-term exposure to altitude. And full acclimatization probably takes about 12 weeks. So if an athlete actually wants to compete at altitude, it's recommended that they actually go to altitude 12 weeks ahead of time before their competition to fully adjust to the changes in altitude. So with altitude exposure, as mentioned, you get a decrease in plasma volume. Your body compensates by increasing secretion of a hormone called erythropoietin. Erythropoietin is secreted from the kidneys, and its effects is to increase red blood cell production. So you get an increase in hemoglobin and red blood cells, and that compensates for the reduced oxygen delivery to your tissues at altitude. So the hemoglobin can pick up more oxygen and partially compensate for that hypoxia. Blood pressure remains elevated. At the muscle level, you might get an increase in mitochondria capillarization and myoglobin with this chronic exposure to altitude. So the studies are mixed with regards to those changes, and that's why I have question marks beside each of these. But this might be a positive adaptation that you get to altitude exposure to increase oxygen utilization at the muscle level. You also get increase in 2,3-diphosphoglycerate. This is a metabolite of glycolysis, and it is released from red blood cells at altitude. So if you have an increase in red blood cell production, you get an increase in this metabolite that's released from red blood cells. Red blood cells strictly rely on glycolysis, so when their activity increases at altitude, you get an increase in release of this metabolite. And I'll cover this in the next presentation that's posted on YouTube. But this increase in 2,3-diphosphoglycerate has an effect to cause a greater release of oxygen from hemoglobin as it flows past your muscle during exercise. But I'll cover that in the next presentation because I'm approaching the time limit for YouTube videos here.